Today, I have the pleasure of presenting Penny Higgins, who is a consulting geochemist and paleontologist with her business Epic Isotopes. Her specialty is using chemical studies of rocks and fossils to infer patterns of temperature, precipitation, vegetation, and dietary preferences. She applies her technical and instrumental knowledge as the laboratory operations supervisor at Eastman Kodak Company in Rochester. She loves science and her cats even more. She founded Mew Mew House, a 501c3 nonprofit that is a retirement and hospice home for cats, which she runs out of her house. With that, I'm happy to present Penny Higgins.
Well, hello. Yeah, okay. I hope you all can see my
Looks
my
great.
screen, and I also have it doing captions on the bottom because I know I can sometimes mumble, and hopefully it'll help for folks who want to better understand what I'm saying. All right. So, reading the rock record, understanding our future. So this is when I talk about understanding our future and looking at the rock record, what I'm talking about is having a better understanding of what we can expect in the future in terms of weather and climate and where are we going. It's a big topic. It's also kind of taboo in some circles. It gets a little nervous. You get a little nervous talking about it. And I'm not going to talk about modern climate change. I'm going to spare you guys that. What I'm going to talk about is how we can understand climate change in the rock record, because in doing so, it actually does give us a much better sense of where we're going with modern climate change. And, well, it's a little scary, but that's okay. I digress. All right. So these are some screen grabs I have. I am maybe slightly obsessed with the weather myself. Whenever there's a thunderstorm rolling in, I get all the alerts on my phone and I go out and I check the radar, and these are around my house and I'm getting excited because it's going to pour rain on me. And when we think about the weather, we think about, like, right now, it's sunny and 56 degrees outside and I want more than anything to be outside. Although I'm enjoying being here, I'm not going to complain. I'm looking forward to days when it's, in the 70s. That'll be a lot nicer. But this is weather. Right, yesterday it was raining, today it's sunny. Yesterday it was in the 40s, today it's getting close to 60. And we can talk about the weather. Big snowstorms, blizzards, hurricanes, those are the weather. When we're talking about climate, we're talking about long-term changes. So here is the long-term high and low temperatures for my little town of Williamson. And so we can have a sense that for any given month, we know that the lowest low is probably going to average around 18 if we're looking at February, or let's look at April because it is April. The lowest low is going to average around 36 degrees Fahrenheit, and the average high is going to average around 56 degrees. That doesn't mean that it can't be higher or warmer or cooler. It just, that's climate. Another way to think about climate is the difference between weather and climate is to think about weather is what dictates what you wear on a given day. Climate dictates what you keep in your closet. So for myself, and I don't know about any of you all, but I've noticed that my closet, there are things that have been sitting in my closet for a really long time that I used to use all the time that I don't use anymore. And so I'm like, why do I still have this? In some cases, it's because I changed states, and I'll tell you, it's winter a lot longer in Wyoming, the state. Asking about Wyoming bottles, I'd like to see that too. But it's a little bit colder in Wyoming, the state, than it is in New York, than it is down in Florida, where I've also lived. So I've been around. But one of the questions we have, and this is kind of a sticking point with folks, is how do we measure global temperature? It's one thing to put a thermometer out and track the temperature outside right now. Easy peasy. We hear about this, we watch the weather on TV. Not a problem. But if we want to talk about global temperature, we have to figure out a way to average temperature for the entire planet, which is Well, it's an interesting mathematical problem, but what I'm showing here is the temperature since 1850 to now. When you see it's gradually going up, this is something that you've seen before. And these are 6 different ways that people in various organizations have calculated this. And I bring this up because the way we can do this is we have temperature stations all over the earth. Some of them have been operating for more than 100 years, especially in North America and Europe. Well, that's all fine and good. But what if we want to go back further than 100 years? Like this infamous hockey stick from Michael Mann. Boy, this one raised some feathers not so long ago, or actually, I guess, anyway, sometime during the turn of the century, of the current century, Michael Mann published this, and he wasn't actually trying to raise hackles or anything with it. But what he did is in this red line, he used thermometers to look at global temperature using all this amazing mathematics where you divide the Earth into a grid and you calculate the average temperature for each grid and then you average all those together. When you get back further, you don't have thermometers. And so what can you use? Well, we use things like ice cores from ice caps in Greenland and Antarctica. We can use tree rings. We can use corals. We can use a lot of things to get back in time. And it was able to get back about 1,000 years, but you notice we get this massive wiggle. That the gray area is the error, the confidence interval. I don't like to say error because it makes it sound like we're wrong. Instead, it's a confidence interval. We're pretty confident that it falls in the middle of this. And we can see, it was kind of steady state and then it started getting hotter around 1900. Okay, well, that's fine. This is great too. But what about even further ago? Let's go back. These aren't thousands of years. These are millions of years. This is the famous Zachos curve. And he's using isotopes from ocean cores to look at global temperature. Actually, in this case, he's looking at deep ocean temperature to infer global temperature. It goes all the way back to when the dinosaurs went extinct. This is pretty cool. And this is where I get excited. Now, this is done using the ocean cores from the Ocean Drilling Project. It's an international project where we drill cores into the Earth's seafloor, collecting sediment. And some of these cores comprise the last 67 million years, which is pretty impressive. Not all of them do, but a handful of them do. And I should say, in each one of these little dots is another core. And this is what the cores look like. And it's like, yeah, it's just so much mud. But we can go through this step by step, and it's a continuous record. And it has these little single-celled organisms with calcite shells that are collected, have been living the whole time that these were depositing. And these little guys with their calcium carbonate shells actually record the isotopes. I'll talk about that in a minute. They record the isotopes that tell us what the ocean temperature was. All right, so isotopes. Let's take a step back, and at risk of sounding like some sort of chemistry lecture, which I'm sure everybody loved taking chemistry back in high school and college, let's talk about isotopes. So it's kind of a term that people like to dislike because most people associate isotopes with radiation. And isotopes are not about radiation. Isotopes, all they are is talking about a single atom and how many extra neutrons it might have in the atom. So if we look at atoms, they have 3 parts. They have the protons, the neutrons, and the electrons. The protons, the number of protons, is what defines the element. So oxygen always has 8 protons. The number of neutrons defines the isotope. So oxygen 16, the isotope is called oxygen 16, has 8 protons and 8 neutrons. There's oxygen 17, which has 1 more neutron. So 8 protons and 9 neutrons. And then oxygen 18, which has 8 protons and 10 neutrons. They all are oxygen. They all behave exact same way as oxygen. but oxygen 18 is a little heavier than oxygen 16, and that'll make sense in a moment. All right, I'm going to attempt this, and hopefully you can hear this. What I've got here for you is a little video that I created ages ago that kind of explains isotopes, and it's cute because it's animated, and I like to share things like this. But I'll explain it again in a minute, and please make noises or wave your hands if you can't hear anything. And there should be sound now. There are two common isotopes of oxygen, oxygen 16 that has 8 neutrons and oxygen 18 that has 10 neutrons. Each of these can be combined with hydrogen to make water, H2O. When it's with oxygen 16, the water is a little bit lighter. With oxygen 18, it's heavier water. We can use these smaller symbols to represent the lighter water and the heavier water. We can imagine a pond or lake or ocean being a mixture of this heavy water and this lighter water. And as water evaporates, the lighter water evaporates faster because it's lighter. So clouds concentrate light water and lakes concentrate heavy water. When an animal comes along and drinks the water, the relative amount of heavy oxygen and light oxygen becomes recorded in their teeth and bones. And when the animal passes away and is fossilized, then this amount is recorded in their fossilized teeth, which we can then extract and analyze and understand past climate. All right, so this is part of what I'm talking about today is part of the Uinta Basin Project. If you want to know more about it, you can always look into the Uinta Basin Project. But let me go back and sort of review what I was talking about. So we have water with oxygen 16 and oxygen 18. The oxygen 16, the water that uses it is lighter, and when it's hot, it evaporates faster. And so that means oxygen 18 is concentrated in the lake, and your clouds and your water vapor concentrate oxygen 16. And anything that's living in the lake or drinking from the lake is going to have the same oxygen isotope ratio as does the water, or it's going to be something we can calculate. So this is pretty cool. We use this notation called the delta notation. You're going to see it. We're not going to worry about what it means. But if you look at this graph, we have this delta 18O. So this is giving us a value for the difference between oxygen and the oxygen 16 and oxygen 18. And what happens here, and this is ocean, what happens with oxygen 18 is it gets concentrated in the ocean. It's just is a little bit opposite how lakes work, because it gets concentrated in the ocean because all of the light oxygen, the light water gets concentrated in ice sheets when there's a lot of glaciation. But when there's not a lot of glaciation, then our isotope values in the ocean become more negative because we have a lot more of the lighter. I'll spare you that any more than that, other than to say we can use oxygen isotopes. We can grow our little foraminifera in waters with different oxygen isotope concentrations, and we can go back in time with these ocean cores, and we can look at the change over time. And what's important to see here when we look at this is, so this is 60 million years ago. I got to move me out of the way. And this is right now. Well, see, right now we should be in a cold spot, but again, I'm ignoring what's going on down here. But we have some interesting blips. We have this little step down when glaciation started. We have this incredible spike here at Paleocene-Eocene thermal maximum, which is a place where a lot of study is taking place, because it took about 10,000 years for global temperatures to rise, maybe 8 degrees Celsius, and then another 200,000 years for things to drop again. And there were some incredible things that happened to mammals there. That's been studied a lot. And then we sort of peaked out in warmth at the beginning of the Eocene, about 50 million years ago. And then as we're dropping down towards cooling and maybe glaciers starting, we have this little blip called the mid-Eocene climactic optimum, or the MECO. So now, all right, this is confusing and I apologize. I don't know why this happened. But on this graph, the oldest stuff is on the left and the youngest stuff is on the right. But everything after this, the oldest stuff is on the right and the youngest stuff is on the left. I'm not entirely sure how that happened, but actually it did. I don't know. But here, this green line is our oxygen isotope curve. Here's a little peak hiding in the orange bar for the Paleocene Eocene thermal maximum. Here's the early Eocene climactic optimum. And here's the MECO. I put a circle around it. More interesting, or interesting on top of that, is this blue line, which is mammal diversity. This is just a count of how many different species of mammal there were. And we notice that there's a huge drop right there at the MECO. And we're like, hold on there, what happened? So we don't know, or before all of this, and we're still working on it, we're uncertain if the reason why diversity drops is because we just haven't found the fossils, or if because this global warming in the MECO caused a big diversity crash. It's a big deal, and this is what we've been funded to do. And enter the Uinta Basin. This is what the rocks look like in the Uinta Basin. This is the Uinta Basin is in the northeastern corner of Utah. It's kind of also close to interesting places you've heard of on the Discovery Network, the Skinwalker Ranch and Blind Frog Gulch or whatever it is. Here's another map of it. This is just the Utah part, and it shows some of the major highways. There's I-70, the town of Vernal, where Dinosaur National Monument resides, the town of Duchesne. And if you go this way long enough, you'll wind up in Salt Lake City. And these different colors are different rock units. The dark blue here is the Uinta Formation, which is just full of mammal fossils. We got big things like brontotheres. If you saw one, you'd be like, holy crap, that's a funky looking rhinoceros. We've also got little monkeys, got all kinds of things in here. This lighter blue is the Green River Formation, and it's famous for all of its fish fossils. This was a lake. And all this orange is the Duchesne River Formation, which is just noted by lots and lots of river channels and some fossilized soils. And it also has some vertebrate fossils. Now, this is the same map. I've changed colors. Sorry. This maroon color, that's the Uinta Formation. And then these three, the brown, the orange, the other orange, and the green, that's the Duchesne River Formation. And if you can imagine making a cross section, cutting right through from north to south, through the Uinta Basin, you'd have this thing on the bottom. It's just a cross section. And what the Uinta Basin is the Uinta Mountains, which is north of the basin, came up and literally pushed the basin down, and then it filled up with sediment eroding off of the Uinta Mountains. And here are the different layers, the same layers, so the Uinta Formation, and then the 3 units of the Duchesne River Formation. What I want to point out here is these numbers right here, which I'm fairly confident you can't see, and that's all right. I'll tell you what they are. So these are 4 parts of the Duchesne River Formation. We have the Brennan Basin member, the brown, the orange is the Dry Gulch Creek, the green is the little point, and this darker orange is the Star Flat. When we look at some radiometric dates that we didn't collect, okay, somebody else did this. These are around 40 million years ago, around 39, another 40 million years, and 34. Now the MECO happens around 39 or 40 million years, and so what this tells us is that the MECO is right here, and it's exposed beautifully. So the MECO lives up here in these rocks somewhere, and we know we've got fossils here, and we can just walk through the layers. Now, at this point, I want to pause, and my role in the Uinta Basin project is the isotopes, the geochemistry. There's a lot to it, but this is a huge project. We have geologists, paleontologists, chemists, palynologists. These are people who study fossil pollen. We have geochemists that are doing other kinds of chemistry besides me, the people doing the radiometric dating. Geophysicists, we're looking at the record of magnetic reversals, because that's another way we can assign ages to things. And it's something we involve students in, both undergraduates, graduate students, and a whole slew of professionals. And somehow or other, we've been doing this even without NSF funding for a long time. But this year is our last year to have National Science Foundation funding. And we're a little nervous about how we're going to continue that, but that's another discussion for another day. But here we are. This purple bar, or this pink bar, is the rocks exposed in the Uinta Basin. So we've got the Mico in there. We've got vertebrate fossils, so we can address this blue line. And the one thing we don't have is the isotopes, at least not yet. And looking at it more closely, this is another graph of the same thing, and I want to point out on the bottom, here's our ages, again, going from the oldest over here to the youngest on the left. This goes from 45 million years ago to 38 million years ago. So right here around 40 to 41 million years is the Mico. And here's the oxygen, or the oxygen core measurement showing the Mico from oceans. This is carbon isotopes. We're not going to talk about that today. And there was a paper that came out in I think in the 20 teens that found the terrestrial Mico, or found the Mico in rocks of Montana, which is exciting to us because we're talking about climate change. And I'll be honest with you, it's hard to imagine how climate change can affect us as humans when all we've got is a record from the ocean. I mean, who cares? I mean, fish and single-celled organisms, who cares? But here it's been found in a terrestrial environment. So we ran out and decided to do the same thing. Now, they did it with isotopes, just as we're planning on doing. This green curve is using an isotopic technique that we don't have access to right now, but hopefully we can get access to that. But this allows you to actually pinpoint temperature, whereas with isotopes, we look at relative changes. Before we found this paper, we had a whole bunch of isotopic data, and it turns out it was all too old to be valuable. So we were a little frustrated with that, but that's okay. We have all this great isotopic data too that's older, and we'll just plug that in when we fill in this. Okay, so when we started this project, and the lead PI on this project has been working in the Uinta Basin since the 1990s. So, and her PhD focused on the primates from the Uinta Formation, and she measured sections and thickness and all of that stuff. But now that we kind of know that the Mico is in the Duchesne River Formation, we've moved our focus. Now, this is a silly graphic, I know, but what we have to do is actually measure the thickness of the rocks. We have to measure the thickness and walk up through the rocks to know how thick they are, and then collect samples to know where the different fossils are coming from, to do isotope studies, to do the magnetism, to do the radiometric dating. We have to actually go step by step, rock by rock, to measure the total thickness of the Duchesne River Formation. And, oops, where'd it go? There it is. So these are a series of rock sections, and you would stack, this would stack on top of that, this would stack on top of that, and so on until you have the full thickness. So we'll zoom in a little bit and a little bit more, and you still can't read it. That's okay. Each one of these divisions is 1 meter. So there's a lot of work that's been done out here. And samples were collected. Every different color, I have a different sample in my home for each one. So I've got hundreds of rock samples here, hundreds of measurements. And for convenience, we've numbered all of these, or used letters. So I, J, K, C, C, it should just be C, but it became C, C, D, E, F, G, and then the last one is H. I tell you that the letters come from the order with which they were measured. So we measured this section first, and then we later realized we needed to go back. But that's important. All right. So this is one of many fossilized soils in the Duchesne River Formation. So we focus on fossilized soil because they grow or it mineralizes this calcium carbonate. So just like the shells of the microorganisms from the ocean floor, we get this calcium carbonate that grows, that the oxygen in the carbonate is in equilibrium with the oxygen of the water, which we can get temperature from. And this is, here's some of the samples. Section G, Unit 52. I've crushed them up. I used an ordinary mortar and pestle. I also have a drill that I use. I have a dental drill that I use. Each sample is pre-treated to get rid of any organic materials, and I do this in my house and in a place where cats can't get to it. And then I drive myself all the way to Cornell, and I weigh out the samples, and they do the analyses. I used to, when I worked at the University of Rochester, I had my own lab. I was in charge of managing it. I lost that job, which is okay. So now I entrust my beloved samples to Cornell. They do a fine job of it. And this is some of our data. Now these are our numbers again, I, J, K, C, D, E, F, G, H. This part is the Brennan Basin member. This part is the Dry Gulch Creek member. And when I collected these, I only took samples like 3 weeks ago to Cornell to fill out the IJK part. So we don't have this data yet. And we can't find any paleosols fossilized soils in the LaPointe member. It's a little frustrating, but we haven't found anything good there. But we have these two units. And what we see, these are all the isotope values. And the way this is arranged, that more positive, which is this is the delta 18O, but a more positive value, it says -2. Yeah, that's more positive than -14. This is warm, lower, this is cold. And if you force Excel to give you a polynomial solution, you get this fun little curve. Now there's a lot of things that are head scratching about this right now. First of all, we have this hump, which is exciting because that's kind of where we expect it to be. We're thinking the MECO is right here, but we don't have anything to tie the other end down here. So I'm excited to see the data. I'm losing my mind. They told me they'd run them at the end of this month, and I don't know, I might just have to start sending them emails every day. But we got some weirdness, like for example, unit D has a bunch of low values compared to C and E. So in order to sort this out, I weighed out these samples again. I weighed out some more. We know this is a bad sample because we ran it twice, and one's up here, one's down here, and there just wasn't any carbonate. And this unit right here, those three that are really stupidly low, those are a rock unit that I lovingly named caffeine-free Diet Pepsi. And it is this bizarre paleosol that's the darkest burgundy color that you can imagine. It's hard as could be, and you can trace it for miles and miles and miles. And it's a mystery. It's a great marker bed, but the isotopes, it's just weird. So, and you'll notice actually that we have a lot of these layers. These units have names like Rocky Road, Old Fashioned, Shirley Temple, Horchata. We, as geologists, we colloquially, conveniently named all of these things after various kinds of alcohol, because we remember them. But yeah, it's one of those things that we had to figure out what to do with those when we publish it. But that's okay. Anyway, so this is a work in progress, and it kind of looks like a lot of noise. But then when I go back to this graphic, and it's hard to see here, but here is our little curve. And when I squish down the scale so things line up properly down here, our little peak actually lines up right in the middle of the MECO. So this is where I am. This is the work I'm doing right now. When I have a spare moment, I'm sitting at home and trying to sort this out, how this fits in here. But we're waiting for some more data here and to clear up this. And then I need to go out to the field and just play. For me, it is a lot of play. It is like my favorite thing in the world. Yes, I do this as a contractor with my company, Epic Isotopes, but this is also my vacation time. I have way too much fun doing this stuff. But it's exciting because we have just a ton to do here. But if we can pin down the Miko, then let me go back to this. We can pin down the Miko, and then we start adding some of the other information, some of the ages that we're getting, some of the magnetometry. Don't worry about that. And then the mammal fossils, which are being done by other members of the research group, we're going to be able to really put our finger on what's going on or what happened during the Miko and how did it affect mammal species. Now, the cool thing is we can do other things with all this data. Each one of these dots is one of these rock samples. So I don't have isotopes for every rock sample, but I do have color data for all of these rock samples. So here's like magenta. And this is using a CMYK measurement if you use Adobe Illustrator or something like that. And you can see a pattern where here's where the Miko is, as far as we can tell. It looks like there's a little bump up. And then it drops off when it goes into the point number. We can also look at grain size, because interestingly, the size of grains in the sediment tell us something about the energy of the environment, how much water was available, uplift, erosion, and all of that. So we can see also there seems to be a peak in grain size there. And we can dig in, we're back to this again, we can dig in a little bit and think about, this is paleomagnetism, because the Earth's magnetic field has reversed itself multiple times over its existence. So we can pin that down a little bit. This is another person's project. And we can also look at the North American land mammal ages, which are a way that we use mammal fossils to assign age to rocks that have mammal fossils within North America. So, and what you'll notice is we like to think that the Uinta and the Duchenian North American land mammal ages would coincide with the Miko, but maybe not. This is like all of the questions, and this is the most exciting part about doing a big project like this. And as it should be, we are coming up with more questions than answers as we go along. But my job is to find the Miko. So, and like I said, we only have funding for the rest of this year. My job is to wrap up the isotopes. For everybody else, we're looking at radiometric dates. We're finishing up the paleomagnetism. We're looking at mammal diversity. And then next year, we're going to try and get more funding to go out there and spend more time doing some work. And if it's something you're ever interested in participating in, you know, we probably have space for you. So thank you. I just want to thank all the folks that are leads on the project. Beth Townsend is the lead PI. Paul Murphy, Tony Frisha, and Laura Stroik are our other principal investigators. And we have a whole slew of people who show up year after year. And this research was funded by the National Science Foundation, so they're doing what they need to do. And if anybody has any questions, me and Richie the cat are happy to answer them.
Very interesting. Thank you, Penny. I do have a question for you.
Yes.
I'm almost a geology engineer because I was a mining engineer by degree, so I learned about rocks. You talked about, one of the things you talked about was can identify some color traits over time. Does the Miko event or stand out specifically on a visible scale, or is it just kind of blended in? Like I know in some sedimentary formations, you see huge variations when you look at the stack of what's going on. Did you see anything like that around the Miko time?
No, that's the thing. When you're standing out there, it all looks the same. It really does all look exactly the same. And it's only this is my little colorimeter. Isn't it adorable? Yeah, I didn't even notice the color differences until I sat with all of the rocks. And we do see some differences, like the paleosols themselves, the fossilized soils are a little bit more purple than the rest of the rocks. But, you know, large scale changes. And what I did with this is I was using a 10-point running average of all of these data points to look at large scale changes. Yeah, it's not obvious. Now, one of the things we could do with color, which could be pretty exciting, they've done in other areas, like with the Paleocene Eocene thermal maximum, is they actually measure color at specific intervals instead of with distinct rocks. They just every meter or so they measure it, and there are repeating color patterns that they can tie to orbital forcings like precession and the ellipticity of the Earth's orbit around the sun and solar radiation. That's something we might try eventually. But right now, when you're standing out there, it's not super obvious at
No,
all.
it looks like too much of eastern Utah, all the same color. I grew up near there, so
Yeah.
it's brown or red or something or gray or something or tan.
Yeah. And we haven't done this for the Uinta Formation, but the Uinta Formation is more orange. And you can see that. Like when you're
Hmm.
looking out over the area, you can see the Uinta Formation is orange and the Duchesne River Formation is red. So, but it still is pretty subtle.
Okay, Rosina had a question for you in the chat. Do most people working on the project live in relative isolation? Are there places or times when scientists and professionals, et cetera, get together when you're not crawling over the rock pile? And that was the last part. The rock pile was my addition.
Yeah, well, we do work. Most of us do not live in that area. We try to gather once a year for a couple of weeks where we come and go and have a large campsite, and then we work together.
Hmm.
So, but most of us, don't live in the area. Well, the person who does the measurement of section lives in Denver, so he's probably the most convenient. There are a couple people who live in Vernal that we've recruited to do some work, and so we pay them and they run out, and do measurements. But we try to go out as a crowd together once a year for a couple of weeks. I don't always make it to those gatherings because I got cats to take care of. But yeah, we do try to get together at the same time and work together so that we don't all get off on tangents. It's really important to do that. We also have online meetings and such to make sure that we're all on the same page as we work through the
Hmm.
project.
Okay, I don't see any other questions. Okay, we have a couple questions in the room, so if you can come up, Heather, and speak to the microphone here, and then we'll get Mr. Peck up here.
Okay. Two quick questions. One, the Miko. Um, is there any theory about what caused the Miko?
Oh, yeah. Well, that Miko is an interesting one. I don't think we have pinned down a cause for it yet. I honestly,
Are
I
there
know.
some theories that general theories that might account for it?
I mean, the things that we kind of look at most of the time, like the Paleocene Eocene thermal maximum, for example, we've tied that to some orbital parameters and also to a sudden burst of melting of these gas clathrates that shot a whole bunch of carbon dioxide into the atmosphere. But the problem with the MECO is that there's not much of a record of it in terrestrial environments, and it's kind of been ignored. So I'd have to dig into the research to look at that. But we definitely want to think about what caused it. I mean, we just don't know at this point. At least I don't.
All right, thank you. The other quick question I have is, it sounds like you're doing some interesting work, research going on, and it's continuing. If we wanted to follow what's happening with your group and the research they're doing, how would we do that?
We do have a website, but probably the best way to follow what we're doing is on Instagram. If you go to @Uinta Basin Project, all one word, we post there regularly about what we've been doing. Videos go up there, pictures. I sometimes post pictures of me sitting in my office drilling rocks. So that's the best place to do that. And we do have a website, but we're really bad at keeping it updated. So I'd go to Instagram first.
Thank you.
So I like the idea that you use a dental drill for some of your work. So
Yeah,
the rocks can't hide from you. We have that dental tool, I bet.
I have had the best conversation with dentists. I used to be afraid of dentists, but now I know how to use a drill as well as they do. So, but I do it a little differently.
Okay. Dave, Dave Peck has a question.
Yeah, hi. So I'm just curious. I've done some Earthwatch projects. Are you familiar with Earthwatch?
I've heard of Earthwatch, but I'll tell you right now, I can't think of what it is they do.
Well, sometimes PIs that work at things like that will take in 10 or 12 people to work with them a couple of weeks and act like gophers, and they learn the project and help with the project.
Oh,
Anyway, I did one in Inner Mongolia about the lost water of the Gobi Desert, and they claimed with their isotopes they could tell how long the water has been traveling underground, and perhaps even where it's coming from. Can you explain how that might be possible?
yeah. Well, I mean, it's kind of a different geochemical tool that is not my specialty, but I know they can use isotopes of some heavier elements to track, and I think it's more of a radiometric thing to track how long the water's been underground, and then they can also look at the various composition of things that are dissolved in the water to know where it came from. So we can trace water motion. I mean, there's lots of ways to do it, but I think in that case they're looking at like I want to say neodymium, but I don't think that's right. It's not research I've ever done. So, but I know we use these kinds of groundwater proxies around New York, actually, trying to think about when we're talking about fracking, and we want to know where the groundwater is coming from that's being affected. You can look at proxies of various salts that are dissolved in the radioactive ones and just see just how long that water was underground.
Well, it seems like the ratio of heavy oxygen or heavy water to lighter water would change over the time, and that the older water should perhaps have more heavy oxygen in it.
Yeah, my guess would be is it would reflect what water was going in at the time it got into the groundwater. So, I mean, if it was a time when there was heavier water, then it would reflect that. So I suppose if you look at ice cores, which is kind of the same thing, you can go down the ice core and take samples, and you can see changes in the oxygen isotopes depending on the global temperatures. So I would guess you would have to somehow take multiple samples in the direction of water flow to see a pattern evolve in that point.
Okay, well, thanks. So just curious about your cat project. How many cats do you have?
I have about 30 cats.
And they're not harassing you right this very moment, or have you locked them out?
This one room that I'm sitting in is my space where cats are not allowed unless I specifically need them. Or, so sometimes I'll isolate cats in here, but this is my my vacation room.
Your cat-free zone,
Yeah.
as much as you love them.
I love them, but I gotta take a break from them once in a while.
Okay, so Martin had a question in chat. I think you covered this before, but if you could repeat it, why does water become heavy or light?
Yeah, so it's not that when we talk about when we look at the ocean is our standard. So there's just a certain ratio of oxygen 18 to oxygen 17 to oxygen 16 in ocean water. And any water that's on the Earth's surface elsewhere has evaporated from the ocean. And because the water that has oxygen 16 in it is lighter, it evaporates first. It evaporates more. And then as it moves across the landscape, when it rains out, it's gravity again, it rains out the heavier oxygen, and the clouds, it gets a little bit lighter. We call this Rayleigh distillation. It's a really interesting process. So we can actually track water masses across continents. I've also used this. I had fun. Remember Hurricane Sandy? That it hit here in Williamson, and I was collecting rainwater while it happened. And that evolved over time. At first, when it was just Hurricane Sandy, it was all like straight up off of the ocean. But then it changed over time because then evaporation took over. Done this with snowstorms. They come in from the West Coast and track across North America, and you can actually see the shift as precipitation comes out and the vapor mass loses the heavier water. So, but it's just a matter of, it's not that the molecule itself changes its weight. You know, when we have the molecule of water, it either has oxygen 18 in it, or oxygen 16, or oxygen 17, and they get divided or separated or distilled from one another because of the weight differences.
Thank you. I don't see any other questions in the chat. Does anybody in the room have any more questions? Penny, I found it very interesting. I like the idea that I probably vacationed in part of that area, or at least been through that Uinta Basin.
Mm-hmm.
And I'm surprised that you don't have people. You didn't mention, people don't go to Vernal that often. Kind of a nice little hole in the wall.
It really is. It's a nice place to spend some time. Although it is kind of a weird place to visit, because it's Utah, and we've had some really interesting interactions because we're a mostly woman crew, and then we'll have one guy with us, and the assumptions that it happens. It's wild. We all have a good laugh about it, but
you and your sister.
Sister wives. Yeah, it's just, they all think we're sister wives, and the one male who's with us must be our husband. Yeah. So we always have a good chuckle about that.
And you set them straight that you're all equals, or you're not beholden to him.
You know what? We just smile and nod. We let them believe what they want to believe because whatever.
Understand.
Yeah.
Okay. Well, again, thank you very much. We do appreciate your very interesting presentation.
You're very welcome. I'm glad to have been here, and let me come back if you're ever interested, because I got other stuff going on as well. Some pretty cool stuff.
Good luck with the cats this afternoon.
All right. Thank you so much.
Take care.
All right. Bye-bye, everyone.
Bye.
Bye. Thank you.
Bye-bye.